Thank you very much. Well, a lot of the results I'm going to show you are done by a young engineer from the Chimie Paris, Céline Bourgeroux. I would like to thank you here. And I would like to show you not only some laboratory results, also some real plant data to support the data the students got so far from the lab. So since almost 3 years we are producing reverse osmosis membranes in Germany, close to Berlin, around 100 kilometers south of Berlin, and we're producing a composite membrane based on polyamide layer. So we're casting the polysulfone layer on the non-woven material. Then we make a polymerization process where the PA is polymerized on the polysulfone to form the selective layer. And then we have a fully robotic winding procedure to make finally the spiral wound modules. So we are the only producer in the European community which making the membranes and the spirals. Well, what does it mean, a high cross-link membrane? Actually, if you now look more into details in the polymerization process, you have two components. This is the TMC and the MPDA. And of a high cross-link membrane is simply that you have a high yield of the polymerization process. If you have a high yield, then you get the structure you see on the left hand of the polymer. And if you have a lower yield, the chlor-carboxylic group does not react with the amino group of the MPDA. It will react with water and form the COOH, the carboxylic group. That is actually the reason the polyamide membranes are usually negatively charged. Of course, you can never get a 100% yield in a polymeric reaction, but our aim was to have the highest yield as possible. Well, if you compare the data sheet of different RO membranes, you always see the same data more or less. The test conditions are 1,500 milligram per liter sodium chloride or 2,000 milligram per liter. The pressure is 15.5 bar. So the test conditions are very similar, and actually also the results, if you compare them on the datasheet, are very similar. But this is simply the reason. This is due to the fact these are normalized conditions. So if you have a low cross-link membrane with a high surface charge, you have also under these conditions a very high rejection, simply due to the electrostatic repulsion. The chloride is repulsed, and therefore the sodium will also not pass the membrane. But as soon as you have real process water with mixed condition, the rejected cations, for example calcium, magnesium, which has a high rejection, form a polymerization, form a concentration polarization layer on top of the membranes. So actually, the anions do not see the negative surface anymore, and therefore you have a decline in rejection. So our aim was that we have a high rejection due to, well, the diffusion process or pore size, and not due to electrostatic interactions. And you may see it also, it's coming up more and more, that some producer of RO membranes are adding not only the sodium chloride rejection on the datasheet, they're adding more. Because simply this simply shows you this is a good membrane. If you not only add the sodium chloride rejection on the datasheet, if you give more information about boric rejection, nitrogen rejection, silica rejection. And since these components are critical, we check these components in the laboratory. So we made a test with boron at different pH. You know, the boric acid is not charged at a pH at below 9.2, then it's getting negative, and therefore you have an increase in rejection. That is the reason you increase the pH before the second pass in the seawater desalination plant. But we could show that we have already a higher rejection also in the lower pH region. And this is simply due to the higher cross-linkage. We have a lower effect of electrostatic interaction, but we have already, due to the lower pore size, a higher rejection also into low pH. And if you we make some calculation, if you will just look at the rejection of 90%, and how much chemicals you could save, we found out that this would be 4.3 milligram per liter caustic you would save if you will focus just on the rejection of 90% of boric acid. We also did the same experiment with nitrate, different pH. Here we also see an increase in rejection. We were a little bit wondering about the drop in the competitive membrane. Actually, another student repeated this experiment and he came again to the same drop. We are thinking there may be some additive with causing an effect we cannot explain, but usually we would expect something similar as you see in the red line in our membranes in the nitrate rejection. So the student could clearly show that we have a lower surface, that we have a rejection is mainly caused by pore size and not only by electrostatic interaction. Since silica is also very important, especially if you're working in boiler feed water, we also check it. And here you have two effects. At high pH, you have of course also the electrostatic interaction, but at low pH, we start the polymerization of the silica. Therefore, you have here also an increase in rejection. But you could see in the pH effect could also show a higher rejection. We could the temperature stability is also very high. Although that is the reason I added also the temperature variant below. We have of course taken into account that the other membrane had a lower flux at higher temperature, and therefore it has of course an influence on the rejection. We're going now to repeat this experiment as the same flux values to support that we have here a higher rejection, but at least you can see that we have a very nice consistent rejection also at changing temperatures. Well, more and more common in the market are the low energy types of membrane, especially if you just want to treat some river water. There we tested it also, and here it was supported that we have here also a higher rejection on boron and nitrate. And we made a comparison with the different design softwares, and we found out that we have a little bit higher pressure compared to the market leader, but we had a 25% higher rejection therefore. So I think it's a good deal to have a slightly higher energy consumption, which I think 1 bar is almost nothing, but you get a much better pyramid quality, especially if you have an ion exchange resin afterwards. You will see it at the changes on the regeneration cycles. The last experiments Lean did was actually to show the rejection of organics. While on the salt side you can always discuss the electrostatic interaction, but on the organics this effect is of course much lower. So they tested isopropylic alcohol with our membranes for low energy and the competitive benchmark, DMF, urea, ethylene glycol, and glucose. And why with isopropylic alcohol and glucose, all the membranes had almost the same rejection. We could show that we, at least with DMF, urea, and ethylene glycol, we have a higher one. We were a little bit surprised about the result because isopropylic alcohol is not a very big molecule, and we were surprised that this rejection was so high. So we made a comparison of different models. One was the model of the volume of the molecule, the other one was a dipole model, and finally the best fit was actually a mixture of these both modules. So of course the size of the molecule and the structure of the molecule has an influence on the rejection, but also the dipole moment of the molecule. Here's a case study. It is a plant in India, Nagada, and it's a UF treatment, then a cartridge filtration, and the TDS is around 600 to 950 milligram per liter. The steam recovery was above 70%, and it was a two-stage system. Well, if we get such water, we usually make a projection first to see how we fit in this plant, because they had some low pressure seawater elements installed, and we wanted to show them that we can achieve the same with our standard brackish water high rejection membrane. So we asked for some information about the plant, make a projection here with the design software. This is of course free of charge downloadable, and we compared with the requirements. Here in this case they wanted to have at least below 20 mg per liter, because as a post-treatment and ion exchange unit, they didn't want to have too much wastewater due to our regeneration cycles. Actually, we could achieve it, and here are some normalization data. The ultra-low seawater elements had just a lifetime of 3 years. The inlet pressure was above 13 bar, and the salt rejection was around 97%, and our elements are now at the moment running below 8 bar and have a salt rejection of 99.3 bar. Well, if you look at the data, you see always a drop down. I think they made several cleanings. They have an issue with the ultrafiltration as a pre-treatment. We are currently supporting them to improve this. Simply 3 years lifetime of a membrane is far too short. We expect a lifetime of a membrane of 5, and actually if a good pre-treatment of an ultrafiltration, anti-scaling, maybe biocide dosing, it can be easily up to 7 years. So currently we are working, improving this process that they can really run 5 to 7 years with these membranes. So finally we could give them an energy saving of 40%, while simply moving from a low energy seawater membrane to a standard brackish water high rejection membrane. We could at least give them in this 1 year period a constant high rejection, and due to the higher rejection of the membrane, they could extend the life cycle of the ion exchange unit. So I showed you some rejection of critical ions. Nitrogen and boron and silica are, I think, the most common ions. We're going to expand it to other ions in the future. We have a high rejection of organic molecules, and this both in combination, I think, is a strong indication that we have a high cross-link membrane with a higher rejection. Although we are just 3 years on the market, we have already more than 10,000 elements installed. So I think it's a very successful story so far. And as I said at the beginning, we are the only producer of RO membranes and elements so far in the European community. Thank you very much.